Okay, so we're going to pick up with number 31. We want to find the designation for the following monosaccharide. So if we take a look at this, we find that 3 and 4 are here and here because we want the carbonyl to be as low as possible. That would be 2. So just in numbering, you have 1, 2, 3, 4, and 5. So if we look at carbon 3, the lowest priority, of course, is the hydrogen. The highest priority is the oxygen. Number 2 is going to be the carbonyl because you're making 2 bonds to an oxygen. And of course, number 3 will be the CH2OH. You need to flip 2 labels twice. So I'm going to flip the 4 and the 2. And I'm going to flip the 1 and the 3. Now that the hydrogen is going away from us, we simply go from 1 to 2 to 3, and we find that this is R. So when you're looking at the answer choices, eliminate both answers that have 3s. And if we do the same thing to carbon 4, again, we find that the oxygen is 1, the hydrogen is 4, and the top carbon is going to be 2 because it's closer to the carbonyl, and the bottom carbon is 3. Again, if we flip 2 labels twice, we can go 4 and 2 and 1 and 3. That's also R. So we're looking for 3R, 4R in our answer choice. And that's going to be answer choice A. Moving on to number 32, we want to find the carboxylic acid that is the least reactive. This is a nice question that if you go on automatic pilot, you can pick the wrong answer. Because if you normally think that an amide is going to be the least reactive, it usually is. But this amide has a leaving group that's aromatic. And the aromatic leaving group is going to be substantively more stable than a normal amide. So we have an acid anhydride, an acid chloride, and an ester. The ester would be the least reactive of these leaving groups. And so the credited response for number 32 is D. All right, in number 33, we're going to have a nucleophilic acyl addition reaction in which we convert the carbonyl to an imine. So let's go back and review that type of chemistry. And so what I'm going to do is just draw the carbonyl. And I don't want to go through the complete mechanism. But I simply want to show you a nice shortcut for converting these two. You're going to lose water, so you're going to lose H2O. So I'm simply going to take one of the H's away, the second H away. I'm going to take the O away, and I'm going to move this nitrogen to where the oxygen used to be. So I get the following imine when the reaction is all said and done. The next step, I'm going to reduce the carbon-nitrogen double bond to a carbon-nitrogen single bond. So if this is my fragment, you essentially are adding the elements of H2, and of course one's going to go to the carbon and one's going to go to the nitrogen. And so you're going to get an amine product. And if we look at our answer choices in number 33, A doesn't work, C doesn't work, D doesn't work, only B works. So the credited response for number 33 is going to be B. So 33 credited response is B. Moving on to number 34. We're looking for a sequence of reactions that will afford our target molecule when we begin with benzene. And so let's try and map this out. So we have a T-butyl group, a bromine at carbon 2, and of course an ether at carbon 4. You know, we can envision doing this several ways. I think one way that would make sense would be doing a Williamson ether synthesis at the very end. So if I had it, actually let's go one better than that. Let's just have an ethyl group. So if I already have this in place, I could brominate next. I could add an ethyl group before I brominate. And then I could have started with benzene. So let's see if we can map all of this out. We want T-butyl chloride and AlCl3 in the first step. Then we want ethyl chloride, AlCl3 in the second step. Of course, we could have the bromide or the iodide. Then we want to do bromination. Again, AlCl3, FeBr3. Finally, we want to do a free radical bromination in the first step, an elimination reaction with T-butoxide, potassium T-butoxide, and maybe some heat. Then we want to do borohydration oxidation. Then we can activate the nucleophile by using NaH. And last, we can do the Williamson ether synthesis with methyl bromide. So let's see if we can pick the best answer that's there. I like T-butyl chloride, then ethyl chloride, then bromination, then free radical bromination, E2 elimination, hydroboration, NaH, CH3Br. B is the best answer for number 34. Number 35, we talked about doing peptide synthesis and some of the inherent complications with peptide synthesis. And so if I have 4 amino acids, these amino acids can, if I have n amino acids, there are n factorial different products. So 4 factorial would equal 20 for us. Simple mathematical problem. And so the best answer for 35 is going to be B. All right, so for number 36, we've got a paracyclic reaction. In fact, to be even more specific, we have an electrocyclic reaction, and it's going to involve 8 pi electrons, 2, 4, 6, 8. Remember that 8 pi electrons means 8 molecular orbitals, 4 that are lower in energy and are bonding MOs, 4 that are higher in energy and are anti-bonding MOs. So with our occupancy, we can put 2 pi electrons into each psi. So lowest energy, psi 1, then psi 2, then psi 3, then psi 4. Psi 4, the HOMO, is the one that we're interested in. There are going to be 3 nodes. Recall that we start with 0, then 1, then 2, then 3. That means we're going to change phase 3 times. And the best way to do this symmetrically is as follows. There's a change in phase between these two, then between these two, and then finally between these two. So your nodes are 1, 2, 3. And notice how this symmetrically divides up the molecule. Now, in order for like phases to interact, we'll have to rotate this orbital clockwise and rotate this orbital clockwise. So this is con-rotary. Okay. And also, look at what's going to happen with the methyl groups. This methyl group will go into the plane or away from us, while this one's going to come out towards us. That's going to be a trans-like arrangement. And of course, the way the electrons are going to move will be as follows. So you're going to trade one of your pi bonds for a sigma bond. So we have 3 pi bonds, and I messed that drawing up. Let's fix that. Need 8 carbons, not 7. And one methyl group comes out, the other methyl group goes in. So matching up, the best answer is choice B, 8-membered ring with a trans-like arrangement. Moving on to number 37. You're looking at the Diels-Alder reaction. And so we want to find the orbital diagram that best describes the HOMO of the diene and the LUMO of the diene. Remember, the diene's got 4 pi electrons. Only these two matter. The lone pair of the oxygen does not participate in the reaction. So we have 4 pi electrons, that's 4 pi molecular orbitals. So we're going to two bonding molecular orbitals, 2 anti-bonding molecular orbitals. So the HOMO is the highest occupied molecular orbital. that has one node. And the LUMO is the lowest unoccupied molecular orbital. That has two nodes. So if we begin looking at our pi MO diagram, the HOMO is going to have one node. And so it is going to change phase only once. And that will be right here. This is a non-bonding orbital, and so we do not need to show this non-bonding orbital in our diagram. And the LUMO is going to have two nodes. And so I'm going to shade in green for the LUMO. And of course, we have this. Here's one node. Here's two nodes. So as we begin to match up our answer choices, LUMO is going to have one node, that's choice A. 38 is going to have two nodes, that is choice C. A for 37, C for 38. Okay, why is the retro deals all the reaction favored at higher temperatures? There are really two good reasons. Number one, you need to break the sigma bonds and convert them to pi bonds. That is not going to be favored thermodynamically, so it must be favored entropically. The higher temperatures provide energy to break the bonds. And number two, the increasing entropy of the retro reaction is entropically favored. So A is the correct statement, and B is the correct statement. C is also a correct statement. It just has absolutely nothing to do with explaining the thermodynamics. That's a kinetics phenomenon. Finally, number 40. Which of the following is most easily deprotonated by hydroxide ion? The answer to that one's going to be C. Let's talk about the cyclopentyl dienyl anion. So in the reactant, we have a non-aromatic compound. However, once I remove a proton to generate the conjugate base, we now have an aromatic compound. So that's a huge stabilizing factor. And so C is the credited response because we make such a favorable product in the deprotonation of the cyclopentadienyl anion. That, of course, is number 40. So I'm going to pause this one, and then we have one more to do where we'll discuss questions 41 through 50.